Hi, my name is Sarah, and my project is on the integration of sustainable cooling technologies in Southern California ice arenas. Ice rinks use massive amounts of energy, most of which are derived from conventional power sources like coal, oil, and natural gas, and cooling is a huge component of this energy usage. This contributes to greenhouse gas emissions, which further accelerates climate change. To address this issue, this study aims to find ways to integrate more efficient and thus more sustainable cooling technologies in ice rinks. The diagram on the right shows the current cooling system that most ice rinks are implementing. The traditional cooling system uses a fluid with a lower freezing point than water to remove and divert heat from the ice rink. Typically, this involves running liquid refrigerant at -9 degrees Celsius through pipes laid underneath the surface of the ice. The liquid draws heat from the ice and is fed to a chiller, which allows the liquid to remain at a cool temperature using outside air and water. So both the plate heat exchanger and the heat pipe system, which will be shown on the following slide, are waste heat recovery techniques. The objective of waste heat recovery techniques is to circulate waste heat developed during industrial processes back into the system. The plate heat exchanger consists of metal plates stacked parallel to each other. Two liquids, one hotter and one colder, are pumped through the plates, and heat transfers from the hotter to the cooler liquid. To know the total heat load to be removed, the amount of ice was determined using the density of water. The heat gained through convection was calculated through the difference in temperature between the air above the ice surface and indoor temperature of the rink. It was calculated that the cooling system would need to remove approximately 1,200 kilowatts to keep the ice at the same temperature and state. Knowing this information, the dimensions of the plate heat exchanger was calculated. A heat pipe system contains a pipe wick structure and fluid that facilitates the heat transfer process. Heat enters the system through one end of the pipe, vaporizing the liquid. Then the generated vapor pressure drives the vapor through the pipe, where the temperature is lower. The vapor loses its heat to a heat sink and condenses back to liquid form. Capillary pressure caused by the wick structure drives the liquid back to the hot end of the pipe. When sizing the heat pipe system, combinations of the various heat pipe metrics were tested and optimized, and the variables included heat pipe length, diameter, angle, evaporator and condenser lengths, and the operating temperature. And something to note was that the evaporator and condenser lengths can only occupy 90% of the heat pipe, so that at least 10% is left for the wick to conduct capillary action, driving the fluid. After these calculations, the optimal combination of the variables for the heat pipe system was determined. The low emissivity paint and atmospheric water harvester, which is the next technology, are designed as supplements because they cannot completely replace the ice rink cooling system. Low emissivity paint is typically used for glass, but can also be applied onto other surfaces, achieving similar thermal insulation. This type of coating minimizes the passage of UV and infrared light and heat energy by reflecting them while still allowing visible light to pass through. The paint itself is made of layers of silver and dielectric materials. By manipulating the thickness and composition, visual and thermal properties of the coating can be controlled. In the context of the ice rink, it would be applied to the roof and other surfaces enclosing the space, such as walls or glass. The application of this technology can reflect 80 to 90% of the heat. This picture shows the schematics of an atmospheric water harvester. The most common method of atmospheric water harvesting is the use of condensing systems. A compressor circulates the refrigerant to the condenser, which the evaporator coil uses to cool the surrounding air. Once the temperature of the air has been cooled to or below the dew point, water condenses out. The water gathered from the atmospheric water harvester can be applied to the cooling system of the ice rink. For the atmospheric water harvester, the amount of water above the ice rink was calculated by converting humidity to mass fraction of water in the air. This ensures that the air is saturated with enough water to be drawn by the device. The results of the calculations indicated that the plate heat exchanger had a unit heat load of 163 kilowatts, requiring 8 exchangers. The total volume for the plate heat exchanger was approximately 1.6 meters cubed. As for the heat pipe system, its unit heat load was 443.6 watts and required 2,360 individual heat pipes of 100 millimeters each. Its total volume was 0.022 meters cubed. The choice between the waste heat recovery methods was the plate heat exchanger. Its upfront cost was a little more than 10% of the cost for the heat pipes. It was also easier to maintain because the device can be easily adjusted by adding or removing plates. Furthermore, it is a lot less tedious to set up the plate heat exchanger since it has less units to install. Between the two supplemental methods, the better suited option is the low emissivity coating. It costs less and contains a relatively easier implementation process. So rather than having to relink the entire cooling system and supply of liquids, the coating simply needed to be applied to the surfaces. So, why is this all important? Well, the results from this study can be used in further research and development in the field of cooling technologies and integration into already existing buildings, structures such as power plants to lower the cost of circulating cooling water systems. Further, construction of rinks can also model their designs based on the results of this study. Thank you so much for listening.